Okay, let's start. Good morning. So this is our final week. We're finally there, at least final week for the purposes of new topics. And so this week is all about PageRank, this algorithm that Google used back in the day for their search engine. And it's all about linear algebra, of course. My plan, hopefully, is to sort of start with an idea and then slowly update it and eventually reach this patented version of PageRank. That before that, I wanted to discuss this ergodic theorem a little bit. I mentioned that this is this idea behind this random surfer model that PageRank is also based on, but still. And even before that, I wanted to mention that you probably have gotten an email about this feedback. Please take some time and fill out that feedback. That would be good to, so you know what works in this class and what doesn't work and everything. Just so that things get better over time. Okay, so there are many ergodic theorems, but the version that I want to discuss is this. It's the least squares version. And I start with an orthogonal matrix Q. In a second, once we discuss this ergodic theorem, I'm going to discuss this idea of Koopman. But let's just first focus on this. We start with an orthogonal matrix Q, and I take it to be d by d. And I call S the null space of Q minus identity. And of course, the null space of this is nothing but the space of vectors that are fixed under Q. The ergodic theorem says this. If I were to take iterates of Q, of this orthogonal matrix, and take their average, the larger this average I take, the better I'm going to approximate the orthogonal projection onto the space. And in the limit, I'm going to actually reach it. So maybe I should write it here. So that over here this is this. So I take my matrix Q, I keep iterating it. I have now n steps starting from time 0. These are matrices, and then I take the average. So I add them up and divide by n. That's the average. I'm telling you, the larger n is here, the average. So the longer I wait to add everything up, the better it gets to the orthogonal projection. Maybe I should also mention what this Frobenius norm is. We had discussed this, but just to remind you. So let me write it like this. So A minus B in Frobenius norm, right? So Frobenius norm was a norm on the space of matrices, on whatever space of matrices. In this case, it actually doesn't really matter that much, but I just needed some way of looking at the distance between that average and projection. So what is this? This is the trace of A minus B multiplied by A minus B transpose. And when you open this up, this really is sort of this standard or natural generalization of the standard norm for a vector applied to matrices. You just think of a matrix as a vector. Every entry is a number after all. So what you can do is this. You can just sum over all entries this. Okay? That's what that is. It's not really that important in this case. All I'm trying to say is that time average is what people would say, gets closer and closer to the orthogonal projection. And here's a picture. So here is S, okay, which is the null space of Q minus I. And I take a vector, V, and certainly if I were to project it like this, and this is orthogonal, this is the orthogonal complement, so this is S perp. If I were to take this orthogonal projection, I have proj sub S of V. And proj sub S is a linear transformation, of course. It's a matrix that is D by D. So the idea is this. First of all, I'm going to look at this piece. Okay? So if this is the orthogonal projection of V onto S, well, certainly this is the orthogonal projection of V onto S perp. What I'm going to do is I'm going to take a vector. I'm going to keep applying my matrix Q. It's going to go to places, and I'm going to keep averaging. Okay? And ultimately, I want this error to go to 0. That's the idea. So first, let's understand that. Let's identify this S perp, because I do need to use this property of Q being orthogonal. So S perp is the null space of Q minus I perp. Okay. Then by the fundamental theorem, this is the column space of Q minus I transpose. But transpose is a linear thing, so I can distribute everything. And so this becomes this. Okay? So if I were to, so now I want to use the fact that Q is orthogonal. So far I didn't do anything. I didn't use the fact that Q is orthogonal. But think of it like this. If W is in the column space of that matrix, this means that for some other vector U, W is equal to Q transpose minus I applied to U. That's what it means. That's one of the definitions of what it means for a vector to be in a column space. Okay. So now what I want to do is this. Now Q is orthogonal, which by definition means that, so let me write it here. By definition, that means that Q transpose Q equals identity, and QQ transpose is identity. So instead of I here, let me write this. Times U. Okay? But then I can factor out Q transpose here and write it like so. Now, Q transpose times U is yet another vector. And this calculation tells you that this W that we started with, which initially was in the column space of Q transpose minus identity, is also in the column space of Q minus I. Maybe I should write it like that. Okay? So any vector in the column space of Q transpose minus I is also in the column space of Q minus I. Well, I can rewind this argument, of course, and conclude that really this column space is the same thing as this. You see here, I really needed the fact that Q is orthogonal. Okay? So now in this picture, I have something very nice happening, right? So I have the null space of Q minus I, and its perpendicular, its orthogonal complement, is the column space of the same matrix. So this is this. Any questions about this so far? I just did some preliminary analysis. I said, oh, I'm going to try to approximate orthogonal projection onto S. Well, orthogonal projections onto S have to do with the orthogonal complement as well. Because one way of doing this, of course, is by subtracting this from this. Right, so this is the piece of V in S, and this is the piece of V that is remaining, which has to be in the orthogonal complement. Okay. So now, if I were to take this, okay, the average of the first n iterates of Q, and I see what is happening. So of course, in this case, matrix multiplication, everything is linear algebraic, of course. So I can think of it like this, or I can think of it like this, right? So I can put the parentheses here. So I can think of iterating the matrix, or I can think of it as, oh, I started with a vector V, and then I keep applying Q to it. And then it goes to places. And then I add all of these, and average gives me a vector, and so on. So maybe I should write it like that. This is the same thing as this. Now, V is the sum of its orthogonal projection onto S and its orthogonal projection onto S perp. Okay. So I can split the sum like so. This is the first piece, and then I have the second piece. Everything is linear as usual, and I can distribute this sum over everything. So I can split it like so. Now, by definition, this particular piece, the orthogonal projection of V onto S, has to be in the null space of this. Okay? Which means, by definition, that if I apply this matrix to this, it's going to be 0. In other words, Q of this is the same thing as itself. So after all, this S is a space of vectors that are invariant under Q, that are fixed under Q. And so what I'm saying is that if I were to apply Q to this orthogonal projection onto S, it's going to stay the same. Well, this is true for any iterate of Q, of course, which means that this thing is nothing but proj sub S of V. Well, what this is saying is that add proj sub S of V n times to itself. So this is nothing but n times proj sub S of V. And then if I were to divide by n, of course, this is going to be merely proj sub S of V. So nothing happens on this side. So okay. On the other hand, this proj sub S perp of V is a vector in S perp, which we just realized is nothing but the column space of Q minus I. Okay? That means that there is some vector, let's call it U, such that V is equal to Q minus I times U. So, sorry, this is equal to that. So this is equal to Q minus I times U for some vector U. Okay. Okay, so we have this. So now the next step is to open this up, because you see I'm adding, so here I'm seeing all iterates of Q from 0 to n minus 1, but then here there's a minus. So my hope is that some things are going to cancel out, and indeed this is what happens. Let's just look at this. I'm just going to write it here. So I'm just going to focus on this piece over here. Okay. I wrote this matrix. I opened it up. That's what it is. And then if I distribute this and this over this, I get the following. So from this, I get q squared all the way up to q to the n. And then from this, I get minus I minus q all the way up to minus q to the n minus 1. Minus I minus q squared minus dot 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 minus q to the n minus 1. But you see there are certain things that are canceling out. This cancels out with this, this with this, this with this. And finally, I'm left with q to the n minus I. Okay? So instead of this expression, I can write q to the n minus I, one matrix applied to u. And of course, I need to keep this 1 over n. Now note that we started with this expression that was on the left here. Basically, I didn't have the vector. I didn't write down the vector there, but you can imagine there being a vector there too if you want. The point is that this piece is really the error, right, of that average against this. Let me write it. And b minus this, so I just took this to the other side, is equal to this. Okay. Let me just erase this piece. Now, instead of using this Frobenius norm for matrices, I'm just going to use the standard norm for vectors. That is to say, here, I'm going to take the norm of this vector here. And because this vector is equal to that vector, the norm of this, the norm of error, is the norm of this vector. So from here, we have and of course I can expand this. Q is orthogonal, and that is why it is norm preserving. Or even before that, I can say that, oh, the norm of the difference of two vectors by the triangular inequality, right, because I have a triangle like this here. So one vector is like this, the other one is this. And this length is going to be this distance exactly. And of course, by standard triangular inequality, this length has to be not more than the sum of these two. Okay? So this becomes like this. Q preserves norms because it's orthogonal. Let me just do that perhaps here. So Q times x in norm squared is q times x against q times x, which is x times x against q transpose q times x. But q is orthogonal, which means that q transpose q equals I, which means this is nothing but x against x squared. Okay? So here I can get rid of this q. And so I would be left with 2 times norm of v divided by n. So you see error, that error that I was trying to control, is bounded from above by an expression that decays with n. So if I were to take n to infinity, this is going to go to 0. And that's the end. So what does this mean? It means that if you start with an orthogonal matrix, and if you're trying to come up with this orthogonal projection, or in other words, a vector that is invariant under your Q, you can do this business that we learned. You would say, oh, like S is this null space of the space. Let me find the basis. Let me find an orthonormal basis for S. Put that in a matrix. That gives me sort of like an orthogonal projection matrix, blah, blah, blah. You can apply Gram-Schmidt, all that stuff. And then you would compute this. You can do that. Or alternatively, all you need to do is to just take averages. You can take your matrix, and so this is a more dynamical approach, as you can see. You can take your matrix, apply your matrix to V a couple times, and take the average of these vectors. If your average is over a long enough period of time, that average is going to be approximately proj sub S of V, is what it's saying. Any questions about this? Now, there's another way of seeing this ergodic theorem. So let me say this is the ergodic theorem of von Neumann. There's a different ergodic theorem that is perhaps more useful. It's called the Birkhoff ergodic theorem. It's slightly more complicated, and we can't really discuss it in this class, but it is there. So let me mention this idea of Koopmanism and how this is actually more general than it looks like. Let me delete that. Koopman was a contemporary of von Neumann. And the main idea of Koopmanism is this. You start with a dynamical system, like we were discussing last week, that is not necessarily linear, right? Most dynamical systems are not linear. Think of, for instance, fluid flow, turbulence, all these kind of things, more complicated things. But it is in finite dimensions, right? So it is, let's say, if in the case of fluid flow or turbulence, everything is happening, everything is mixing in a bounded domain that is of finite dimension. But it is nonlinear. So Koopmanism is all about taking a nonlinear dynamical system that is finite dimensional and turning it into a linear system that is infinite dimensional. So you trade linearity for finite dimensions. Finite dimensional system, dynamical system, turn it into a linear infinite dimensional dynamical system. It's a whole theory, of course. And one of the things that is very popular is to do this. You start with a nonlinear system, turn it into a linear system in infinite dimensions. I still haven't told you how this is actually done. I'm going to mention it a little bit, but I'm not going to go too much into detail. But once you have a linear system, it's an iterates of a certain linear transformation. And by now we learned that eigenvalues, or more generally the spectral data of a linear transformation is an important thing when it comes to iterations or dynamical systems. So now what you can say is, oh, I have this linear dynamical system that is infinite dimensional, but because it is linear, I can talk about its spectral data. And so perhaps that spectral data says something about the original nonlinear system, and it turns out that this is true. You get to say things. It turns out to be important. And further, perhaps if you're lucky, you can say, oh, you know, like this system is infinite dimensional now, but perhaps I can reduce my dimensions a little bit. Maybe I can make it finite. There are certain techniques to do that, but this is, of course, course of its own. Spectral data of the linear system says things about the original system. Now, typically, instead of looking at iterates of an orthogonal matrix, what you do in Koopmanism, because your space is infinite dimensional, you look at an orthogonal transformation of a certain infinite dimensional system. There's an analog of this ergodic theorem in that setting, but I didn't want to get too much into defining orthogonal transformations and blah 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 in infinite dimensions. That's why I just stuck to orthogonal matrices. But in any event, so let me just mention how this linear system is obtained. At least give some idea. So the type of systems you should think as sort of weather forecasting. Right? So weather is a deterministic system after all. There are certain differential equations that tell you what is happening when. The problem is that there are so many variables that it is virtually impossible to compute things. So you need to do things. You need to do something. So, and of course it is nonlinear. So let's think of it like this. So let's say that my original dynamics is like this. I have this transformation that is not linear, but it sort of encodes the time progression, the time evolution. And let's say that I have a nonlinear space. So it's like this. Let's say it's like a blob. Maybe you don't even know how it looks like. But you know that it is finite dimensional. Maybe it has like holes or something. That's your so-called phase space. And so just like iterating a matrix, you can iterate a transformation like this, more general transformation. You start at a point, goes to f of x and so on, f squared of x. One thing you need, and this too can be generalized, but let's just stick to this. Let's say that the volume is preserved under your transformation. Say f preserves volume. This means the following. Because the system and even this space is mysterious, what you want to do is you want to come up with certain observables. These are your measurements, so to speak. An observable is basically a function from your mysterious space into real numbers. The point is that it's something you can integrate, okay? So you want to say, oh, what is the average value of this observable? You have some sensors, let's say, and it is just reading off some data to you. And of course, you can look at the average. F preserving volume corresponds to this, okay? So this is the average tomorrow, right? So I iterated my map by 1. So I let time progress by 1 unit. I'm saying this has to be the same as this. The average tomorrow equals the average today. So space average, of course. Tomorrow equals space average today, no matter what my observable is. Right? I can just come up with a bunch of different observables. I'm saying no matter what my observable is, I want this equality to hold. If you have this, then it turns out that you can look at a certain linear subspace of the space of functions on M, taking real values. We discussed how this is a linear space. Even though M is not necessarily linear, certainly you can take 2 observables on it, add them up, or scale one observable by a number, which means that the space of observables is a linear space. Of observables, which in our notation was f from M to R. Let me just call it O, is a linear space and further, it's an inner product space. It has an inner product, and it is given, that inner product is given by integration. So if I were to take 2 observables, I want to think of the angle between them, so to speak. Or I want to think of how correlated these 2 are. I could say, you know, maybe observables are orthogonal and so on. So all you need to do is this. Take their product, and then take the average of that product. Okay, this is an inner product. And of course, once I have this, I can talk about orthogonality. I can say, oh, this observable is orthogonal to this other observable. It's sort of detecting something completely perpendicular to what this other observable is detecting. So this is an important thing to be able to do. And so I told you the original space, the infinite dimensional space. I still haven't told you the linear dynamics. The linear dynamics is this. So the Koopman operator associated to the original nonlinear dynamics is this. So let's denote it by Q. Okay, if you want, it's Q sub F. Take a vector, it's a function, and now look at this. So this is just, instead of applying your observable to X, you let time pass by 1 unit under your original dynamics, and that's your new observable. And so you see, this gives you a linear dynamical system that is orthogonal. Linear and orthogonal dynamical system. And of course, this space of functions, right? So function space is supposed to be infinite dimensional. It is infinite dimensional. But having something linear is so useful that you'd rather have something linear as opposed to something nonlinear, even though the cost is having infinite dimensions. There's a bunch of theory as to how to deal with this, of course. Okay. The past 10, 15 years, this Koopman operator methods have been in vogue, especially among mechanical engineers, people who are sort of like looking into things like turbulence. And of course, the spectral data of this transformation. In general, of course, this is an infinite dimensional space, and the theory is more complicated than what I've discussed. But certainly, there's an ergodic theorem for this Q sub f, and we can do things. So you see, this ergodic theorem for applied to this guy gives you ultimately an observable that is invariant under time. So it's a time, so this orthogonal projection produces for you an observable that is invariant under time. Even though your dynamical system originally is very nonlinear, very complicated. It tells you, oh, if you just look at this and that number is not going to change under time. So it's an important thing, being able to come up with invariance. So maybe I should record this. Yes. Yeah, so one problem, for instance, you can think of it as the three-body problem. You have three objects with mass that are moving, and they attract each other based on only the inverse square law. Right? The closer they get, the more they attract each other. This is an unsolvable, this is still an open problem, by the way. We still cannot solve this because it is so complicated as a differential equation. So you would need 6 dimensions for this, more than 6 actually. So for each particle, you would need 3 dimensions for position, 3 for velocity, so that's 6. You have 3 particles, you need 18 dimensions. So that would be sort of like a phase space in that situation. So you want to put every single piece of information that is required to be able to solve it, at least in theory, into phase space. Yeah. Okay, so ergodic theorem applies to Q sub f, and it tells you a way to come up with an observable that is invariant under your dynamics. And you can imagine how this could be useful, right? Because in finite dimensions, we had this space of fixed vectors, and it's a finite dimensional subspace. But in the case of infinite dimensional subspace, you can still think about like orthogonal projections from a geometric point of view, but it is harder to handle, writing down expressions and so on. This iteration is much more straightforward, and it produces an observable, let me call it psi, that is invariant let me say, okay, I'm not going to say anything. It's not exactly invariant. There are certain fine print that I'm not saying. Invariant under the nonlinear f. And the way you do this, ergodic theorem says, is that take any observable whatsoever. It's very intuitive in a sense. Take an observable, take averages of it over a long period of time. Eventually that should stabilize, that number should stabilize. Okay, so so look at the point and read off what this observable says, any observable says at time 0, and then what it says tomorrow at the same point, and so on. Add all of these numbers up and then divide by n so that you have an average. This is pretty much invariant under my dynamics, is what it's saying. So this invariant observable is approximately this average. And this is yet another way of sort of summarizing the things. Now, let's connect this to PageRank. In PageRank 2, we're trying to come up with a fixed something, ultimately. I'm going to remind you all that tomorrow. But you have a dynamical system. I didn't say this before, but this we had a graph that represents a network of web pages where the dots are your web pages and your links, your edges are your hyperlinks. And what you want to do is you want to figure out which of the web pages is the most important based on the connectivity structure of your network. That was the main goal. And I mentioned this idea of this random surfer model. I said you start at any point, and after each unit time, you look at every single hyperlink you can find at a given web page, and you just choose one of them at random. And then you keep going like this. So if you let your random surfer surf for a long period of time, the amount of time this random surfer is going to spend at any given web page is going to be the page rank of that web page, I told you. Underneath this expression, even though we're not going to sort of discuss page rank necessarily from this point of view, or when it comes to calculations, at least for us, we're not going to be sort of iterating and stuff like that. This random surfer model underneath it is still an ergodic theorem. You have your dynamical system, you iterate it, and somehow averages converge to the invariant thing you want. Okay, there are certain details about this, but I think it's a good place to stop. Tomorrow, we'll get back to PageRank. Okay, thank you. Okay, let's start. Good morning. From week 7, we had this Gerschgorin theorems that I couldn't cover at the time. Today we're going to need it because we're going to start talking about Markov chains. So I thought it would be good to just discuss it first. And Gerschgorin theory, what people call Gerschgorin circle theorems, is all about approximating eigenvalues with minimal work, let's say. So the idea is this: if you take a square matrix, so obviously computing eigenvalues is a chore, right? It's a computation. But Gerschgorin says the main idea is that the diagonal entries of a square matrix are approximations to eigenvalues of the matrix. How good of an approximation we're talking about then becomes a matter of the off-diagonal entries. In particular, if you have a diagonal matrix to begin with, we know now that the eigenvalues of a diagonal matrix is the entries in the diagonal. So for a diagonal matrix, Gerschgorin theorems just allow you to say, with 100% accuracy, the eigenvalues are the diagonal entries. If your matrix is not diagonal, it says, oh, up to some error, your eigenvalues are the diagonals. So if I were to start with an n by n matrix, I need to define these Gerschgorin sets or disks. For each row, you have 1. So I runs from 1 to n. And I'm going to define these to be certain subsets of the complex plane, where the spectrum lives. I'm essentially trying to capture the spectrum of the transformation. So gamma sub I of A is the set of all those complex numbers that are not more than this number away from the diagonal entry at the ith row. So this AII is the diagonal entry in the ith row, and the remaining, this sum over here, is really the absolute value of, or the sum of the absolute value of the remaining entries. Right, so j not equal to I, I'm adding up all the aij's in absolute value. And then, of course, I can take the union of all of these and call this the Gerschgorin set, gamma of A. The first theorem says this, that any eigenvalue of A is in some Gerschgorin set, is in some Gerschgorin disk. And if you wanted to, if you're into abbreviating this, you can just say that the spectrum of A is included in gamma of A, the Gerschgorin set. And then the second theorem says that if you have S many Gerschgorin disks that are disjoint from the remainder, then those S many Gerschgorin disks contain some amount of eigenvalues. And it says that if you add up the algebraic multiplicities of those eigenvalues, they add up to S. So here's an idea. Here's an example. This is a bunch of theorems. So let's look at this, for instance. So here's one example. So consider this matrix. So this, in a bit, we're going to start calling a column stochastic matrix. As you see, each column has a bunch of entries, and they all add up to 1. And you know by now that any such matrix, whenever the column sums or the row sums are the same number, that number is an eigenvalue. So from that, I can immediately say that this has 1 as an eigenvalue. And of course, I can compute the other eigenvalue as well. You've actually computed this in one of the previous problem sets. This is a matrix of the form P, 1 minus P, Q, 1 minus Q, of course. And then you computed, for instance, that the spectrum of this. So one of the eigenvalues is 1. The other one is, do you remember? 1 minus P plus Q, I think. So in this case, maybe it's something else. But in any event, in this case, it is something else, some other number that is less than 1. So Gerschgorin says the following. Look at, so don't compute anything, look at the diagonals. Okay, so gamma 1 is the Gerschgorin disk corresponding to the first row. Let me write this, because this is very useful. I just learned this a couple of weeks ago. This Gerschgorin theorems was suggested by our course coordinator to discuss. So I didn't know anything about this. It's pretty nice. So all those complex numbers such that this has to be closer. So the distance between this complex number and this number cannot be more than this number. So z minus 0.95 in absolute value, or in modulus, is not more than 0.03. Okay? And then I have the other one as well. Now I have all those z's such that the modulus between 0 and z and 0.97 is not more than 0.05. Okay? So now I can draw these. So let's do it like this. So this is our picture for the spectrum. This is the unit circle. I want to zoom in, right, because the numbers are kind of finicky. I'm going to zoom in to this little piece, and I'm just going to draw that piece. So let me just do it like this. So this is 95, 6, 7, 8, 9, 1. That's 1. This is 0.95. And what else do I need? So I need to go 3 less. 4, 3, 2, 1, 0.9. Okay, so this is 0.9 in the real axis. This is 1 in the real axis. So this point is exactly this point. 0.95, I need to draw the disk of radius 0.03. So 5, 6, 7, 8. And 5, 4, 3, 2. Yes, this. So now you draw the disk. That's your gamma 1 of A. Okay? And then what is the second one? For the second one, maybe we should use a different color. Let's use orange. So this is 5, 6, 7. This is 0.97. I need to go 5 up or down. So 7, 1, 2, 3, 4, 5. So this, and then the other one is somewhere there. So the other Gerschgorin disk is going to be like this larger thing. So the circle theorem tells you that the eigenvalues are inside this union of these two disks. In this case, this gamma 1 is a subset of the second one, so you can just ignore this, but everything is in here, and certainly one eigenvalue is here. Okay? So it's a pretty nice thing to be able to do. Minimal calculation, as you can see. I mean, there's still some calculation when you're looking at higher dimensional matrices, of course. You need to add things up. But compared to the actual calculation of eigenvalues, it's pretty good. So here's another example. One minus 1, 1 minus 1. This is not invertible, of course. Its rank is 1, which means that 0 has to be an eigenvalue. So that's one of the eigenvalues that I know. But let's figure this out using Gerschgorin again. So the first disk is going to be centered around 1, and it's going to have radius 1. Okay. And the second disk is going to be centered around minus 1. Again, it's going to have radius 1. I mean, these are of the same type. So this is the first, this is the second, and so this is gamma 1, this is gamma 2. Which tells you that you really need to think of the boundary, right? You cannot just say strictly less, because I know that one of the eigenvalues is 0 here. Okay? It could be on the boundary. But of course, this also gives you, the Gerschgorin theorems give you a nice way of, or perhaps a convenient way of distinguishing when a matrix is not invertible, right? Because you can take a matrix, look at the Gerschgorin disks, and if none of these disks contained the 0 in the complex plane, that means that your matrix is invertible. So let me write it here. If no gamma I contains 0, then A is invertible. Okay. Here's another example, slightly more complicated. Yeah. By the way, you can use complex valued matrices as well. It doesn't matter for Gerschgorin, but because we're not really looking into complex valued matrices, I'm not discussing that. So look at this. Let's look at the 3 by 3 now. It's going to be 4, 1, 1, 0, 2, 1, minus 2, 0, 9. Okay. So I've already put this in on into Wolfram alpha, and I know the eigenvalues. Let me just say. So one eigenvalue is 8.485 and so on. The other one is 4.631 and so on. And the other one is 1.882 and so on. So let's see that the Gerschgorin circles really allow us to sort of predict, at least to some extent, where these eigenvalues should be. And you see, in this case, they are real eigenvalues, even though the matrix is not symmetric, which can happen, of course. So again, I look at these entries, diagonals, and then the off diagonals are going to give me the accuracy of the approximation. So let's write it like this. So this is the real axis in the complex plane. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So if I were to look at the first Gerschgorin disk, it has to have radius 2. Okay? So the first disk is going to be green. So it's centered at 4. And it's going to have radius 2. So it's going to be like this. That's my first disk. My second disk is going to be centered at 2, and it's going to have radius 1. Okay, so it's like this. And then finally, my third disk is going to be at 9, centered at 9. It's going to have radius 2. And let's draw it using yellow. Okay, so I just drew the boundaries, but everything inside is included as well. And so compared to these, let's put these down as well, the actual eigenvalues, or the eigenvalues that Wolfram gives. So 8.48 is somewhere here. 4.6 something is here, and then 1.8 is somewhere here. Okay, so this is how it works. And you see here, you see the second circle theorem acting as well. On the left, I have one cluster of Gerschgorin disks that is disjoint from the rest. Okay? Now, Gerschgorin tells you, the second circle theorem tells you that in this big thing, let me just think of it like this. So in this union, Gerschgorin tells you that somewhere in here there are some amount of eigenvalues. It doesn't say that they have to be distinct, but it says that ultimately the algebraic multiplicity is going to add up to 2 because there are 2 disks here. Okay? And here it says, oh, this is one disk. So here it says, and it is disjoint from the rest, the algebraic multiplicity is going to be 1. Okay? So that's the idea. As you can see, this is lots of fun, and I think it's very useful too. Any questions about this? I don't think I want to spend too much time on why this is true. It's not that complicated, but we haven't proved the spectral theorem. Certainly we're not going to prove Gerschgorin theorem. Okay, this is how it goes. So let's now apply it to more general situations. For instance, if I were to take a permutation matrix, I can immediately say, using Gerschgorin theorem, that any eigenvalue of it is going to be not more than 1 in modulus. Oh, let me mention, of course, the spectrum of A is the same thing as the spectrum of A transpose. Eigenvalues don't change when you take the transpose, which means that if you want it, you could also look at sort of Gerschgorin disks of A transpose. Maybe that gives you better estimates and stuff. There's a bunch of different things people do, but let's not spend too much time on this. If I have a permutation matrix, by definition, that means that any row, and so it's a square matrix, it is invertible, any row and any column contains exactly 1, and the rest is 0. Let me remind you. Any row and any column contains exactly 1, and the rest is 0. Okay, so let's think about this. So in order to apply the Gerschgorin theorem, I'm going to look at the diagonal entries. Diagonal entries for a permutation matrix is either a 1 or a 0. Okay? So let me just look at PII, right? The ith diagonal entry. Either it is 1 or it is 0. If this is 1, well, in the ith row, this is the only entry that is 1. That means that the remainder are 0, which means that the ith Gerschgorin disk is going to have radius 0, and it's going to be centered at 1. So it's just telling you that this is an eigenvalue. Otherwise, if the ith entry in the ith row is 0, well, in the same row, there must be some other entry that is 1, and everything else is going to be 0. And this means that the ith Gerschgorin disk of A is going to be centered at the origin, and it's going to have radius 1. It's the unit disk. If that is the case, that means that this Gerschgorin set, the union of all Gerschgorin disks, is nothing but unit disk. Well, the spectrum of A, or P rather, should be included in the Gerschgorin set. Well, that means that the spectrum is in there somewhere. Okay? Okay, that's pretty useful. I don't know what eigenvalues are, but I know that none of the eigenvalues are going to be more than 1 in absolute value. Any questions about this? Let's generalize this idea then and combine, in a sense, or rather, let's generalize this permutation idea along this idea of the stochastic matrix. So here's a definition. Here are two definitions. A probability vector is by definition a vector. It has to be a vector. Is a vector, doesn't matter how many dimensions, but it has to have certain properties. One of them is that I don't want any of these to be less than 0 or more than 1. And second of all, I want them to add up to 1. Such that Pi for any I is between 0 and 1 included. And second, I want them to add up to 1. You can imagine why it would be useful to call this a probability vector, because this is sort of like this. You have n options, okay? And this probability vector, once you have one, tells you what is the probability of choosing any one of these. So let me say Pi or P1 tells you what is the probability of choosing the first option, and so on. So of course, even though I use the word probability, there is a certain sort of determinism related to this. Or rather, it's kind of murky, figuring out what is random and what is not random. And this will be the case in the context of PageRank also. But of course, so let's imagine this. In dimension 1, if n is 1, I have only one probability vector. Because I have one entry, it has to be 1. That's not that interesting. So if you have one option, that means that your model tells you that with 100% probability, that's what's going to happen. So this is your real line, this is 0, and this is your probability. 1. If n is 2, now you have two different states. It's sort of like a coin, okay? P or P1 is the probability of heads. P2 is the rest. It's the probability of tails. So in this case, what's going to happen is that I'm going to have two entries. They're going to be between 0 and 1, which means that my probability vector is going to be in the first quadrant in the plane. It's going to be here. And I want them to add up to 1. So P1 plus P2 equals 1. That's the equation of a line, of course. And it turns out to be this. This is 1, 0. This is 0, 1. any point on this green line is a probability vector. And if you're right in the middle, 1 over 2, 1 over 2, that's what's called a fair or unbiased probability or uniform probability. So let me do one more thing. N equals 3. Now I need to go one more step, one more dimension higher. So now I'm in 3 dimensions. And this time I'm going to see a triangle, right? Any point on that triangle is, it tells you a probability, and so on. Of course, these shapes are called the standard simplices. So this is also called the standard simplex of 0 dimension. This is called the standard simplex of 1 dimension. And this is the standard simplex of 2 dimensions. No, this is more general. Yeah. Yeah, triangulation is, so this is related to triangulation as well. If you want to model a shape, you sort of like turn it into a bunch of the small simplices put together, essentially. Yeah, I wanted to sort of mention this connection between probability and these simplices. So elements of, so points and simplices are probabilities and vice versa. Okay. So then I can, oh, I erased it, but so this matrix that I just erased is a matrix, each of whose columns is a probability vector. Okay? Whenever you have a matrix like that, you call it a column stochastic matrix. So here's another definition. A square matrix S for stochastic, is called stochastic, means just random. There's nothing random about it really, but it models something random. Is column stochastic. If each of its columns is a probability vector. Okay. Now let's interpret this. So this example that I erased, let me just write it again here. I'm just going to write it here. So 0.95, 0.97, 0.03, 0.05. As you see, both of its columns are probability vectors. So this is stochastic or column stochastic matrix. Now, why would you want to think of this as something related to probability or something random? Because of this. You imagine 2 different states, okay, and you're thinking of these numbers as transition probabilities. So let's say that you have one state which represents Salt Lake City, and you have another state which represents, let's say, LA. Now interpret this as, so this is a dynamical interpretation now. Interpret this first number as the percentage of the population in Salt Lake City that next year is going to stay, is not going to move to LA. Okay, so I have an arrow like this, and it has a weight which is 0.95. And I'm thinking of this, the remaining, the probability of moving to LA. So there's a bunch of ways of interpreting this. One way to say this is that either this is the probability of a person living in Salt Lake City staying in Salt Lake City. So this is, the probability is 95. Or you say, oh, out of the total population in Salt Lake City, 95% of it is going to stay in Salt Lake City next year, and 0.05% is going to move to LA. And likewise, this is going to be the probability that you stay in LA next year, and 0.03 is going to be the probability of moving to Salt Lake City next year. Okay, so it is more probable for a person living in Salt Lake City to move to LA than vice versa, according to this random interpretation that I came up with. Okay, so this is why you can imagine how you can imagine that these are related to sort of some random processes in a sense. We're not going to go too much into this randomness stuff, probability and everything, although it is a very beautiful subject. So this is that. Any questions about these so far? Okay. So now applying the Gerschgorin theorem to a stochastic matrix. Oh, let me just say this. Of course, a permutation matrix is a stochastic matrix, right? Because each column has either a 0 or a 1. So it's a more deterministic, if you want. But of course, not every stochastic matrix is a permutation matrix. But in any event, you can apply the Gerschgorin theorem to a stochastic matrix in general and come up with something very similar to that. Let S be stochastic. And as usual, I'm looking at the ith Gerschgorin disk. So let me write this. Ith Gerschgorin disk is going to be the set of all those complex numbers such that the distance between z and the ith entry of S is bounded from above by the sum of the rest. Okay, I'm going to look at S as transpose. Because I don't know necessarily that if I have a stochastic matrix, the rows are probability vectors, right? So in this case, the rows are not probability vectors, only columns are. But I can apply Gerschgorin to columns of a matrix if I want it. So that's what I'm doing. So this is the sum of all those entries in the, so now it is ij, so ji in absolute value. But of course, I don't need to put absolute values here because any entry of a stochastic matrix is a positive number or non-negative number. So I can just delete this. And further, the sum of the rest is going to be exactly 1 minus this. Okay? which means that the ith Gerschgorin disk is going to be of the form of the following form. So first of all, it's so this SII is somewhere here between 0 and 1, right? Because it is part of a probability vector after all. Maybe I should draw it using a different color. This is the disk of or circle of radius 1, and I'm saying that have the center here and have your radius be whatever the remainder here is. So which means that once you draw this Gerschgorin disk, it's going to be tangent to the unit disk. Okay? And it doesn't matter what what index I you're using. It's always going to be like this. Which means that ultimately, again, the any eigenvalue of any stochastic matrix is going to be included in the unit disk. So let me write it like this. If lambda is in the spectrum, so if it's an eigenvalue, then lambda in modulus is not more than 1. While combining this idea from one of these problem sets where you figured out that if the row sums of a certain matrix is the same number, that number is an eigenvalue. I also have that 1 is in the spectrum, no matter what your stochastic matrix is. So you have one eigenvalue here. You know it is here. Okay? And then you have a bunch of disks that tell you approximations. Okay? The point of being able to apply all this theory to PageRank is going to be that you want to associate a stochastic matrix to your network of web pages. And you want it so that 1 is an eigenvalue and its algebraic multiplicity is 1. Okay? Whenever you can do that, PageRank works really well. I still haven't reminded you what this PageRank was all about. I'm going to get to that in a second, but I just wanted to relate. Okay? Any questions about this?
I was just wondering, so like, since transpose preserves eigenvalues, why don't they like do this and then take the transpose and then do it and then take the intersection of all of the circles?
Yeah, you can. Yeah, you can do even further, because another thing that preserves the spectrum is, of course, similarity transformations. So you can indeed do that and come up with a nice matrix and nice matrix, let's say P, and instead of looking at S, look at the Gerschgorin disks of P as P inverse. If you can come up with a nice P matrix, then those diagonal entries are going to be perhaps much smaller. Yeah. But of course, there's a trade-off there, because at the best situation, you have a diagonalization actually. But the problem is that diagonalization is hard to compute. So there's like a trade-off. Yeah, yeah. There's a bunch of like very nice sort of algorithms around this and like ways to sort of come up with better approximations and so on. This is just like a taste of this whole Gerschgorin theory. And in some situations, you can also apply it to infinite dimensions and so on. So infinite dimensional matrices and everything. So pretty nice. Any other questions? Okay, so let me give the definition of a Markov chain now. Now that you have a stochastic matrix, at least for our purposes, a Markov chain is nothing but a dynamical system where your time evolution is given by a stochastic matrix. This is not exactly how it is defined generally, but this is how they define it in the book. And I thought to define it more generally, we need to spend more time with probability. And I don't think we have time for that. So let's just stick to that. The main idea, I'll tell the main idea in a second. A Markov chain is a dynamical system. So it's the iterates of a matrix, of a square matrix, where the matrix is stochastic. It's the dynamical system that is the iterates or powers of a stochastic matrix.
Is that basically saying, like, given a stochastic matrix, like this enumerates, like, taking that matrix to the nth power?
Yeah. Mm-hmm. Yeah. So the adjective that you should keep in mind when it comes to Markov chains is memorylessness. Okay, so you have a time evolution, and it is to some extent probabilistic, but in a sense it is deterministic too. You see, because I'm just iterating a matrix after all. The state tomorrow only depends on state today. Okay, so this is this idea of being memoryless. So certainly this, what I discussed here is a Markov chain. Okay, so this says, oh, if I'm in this state with this probability, next year I'm going to be here, and with this probability I'm going to switch over. So this doesn't say, for instance, oh, I've lived all my life in Salt Lake City, and that's why I need to change. There's no such thing. Just like you look at where you're living this year, and based on that, you make a decision. And of course, let me also mention, if I were to multiply S with itself, I would have a bunch of different numbers. These numbers would correspond to two-step transitions, right? So if I were to multiply S by itself, it would be some other numbers. The number I would see here would be the probability of staying 2 consecutive years in Salt Lake City, according to this model. Okay, so here's a more interesting and more important model. And this is called the Ehrenfest dog and flea model. You have a bunch of dogs, okay, and each of them have some amount of fleas. Let's say that you start with the same amount. And let's say that you have 2 dogs. Okay. Okay, I'm just going to draw people. Okay, I have 2 people. And each of these people, they're living in a close proximity. They have the same amount of fleas. Okay, so let's say that both of them have 3 fleas exactly. In total, I have 6 fleas. My Markov chain, that is to say my dynamical system, is this. at each time progression, one of these 6 fleas at random switch sides, jump to the other guy. Okay? Let me not write it down. And what are the states? The states are the number of fleas here compared to there. So I have a bunch of states. So 0 against 6, or 1 against 5, and 2 against 4, 3 against 3, 4 against 2, 5 against 1, and then 6 against 0. Okay? So these are my states. So the left number corresponds to the number of fleas that this left guy has, the guy on the left has, and the number on the left corresponds to the rest. So if I were to start here, so let me say that jumping, so a flea jumping to the other side is always 1 over 6, okay? But you see the distribution changes, the probabilities change based on how many fleas are collected to one side. So this is supposed to be a model for, it's also an important model for heat diffusion, okay? So this is supposed to sort of exemplify the so-called second law of thermodynamics. Heat always flows to the colder side. So if you start here, let's say that you started here. Of course, with 50% probability, you're going to switch to this side. 50%, you're going to switch to this side. So let me just say 3 over 6, 3 over 6. If you're here, you see it is more likely to get a flea from the right to the left than vice versa. I guess I'm out of time. We'll continue talking about this tomorrow, but that's it for today. Thank you. Okay, let's start. Good morning. So today, finally, we're going to start talking about PageRank, or the details of it. PageRank is a specific application of this theory of Markov chains, but before we start talking about PageRank in more detail, I wanted to go through this other example of a Markov chain. And even before that, I wanted to mention this a correction that I think I made a claim yesterday that I think was erroneous. We had a stochastic matrix, 2 by 2. I didn't write down the numbers, but you can imagine the numbers being there. So P, 1 minus P, Q, 1 minus Q. Recall that the stochastic matrix is a square matrix, each of whose columns are probability vectors. And by which, I mean it's a vector, each of whose entries is between 0 and 1, including 0 or 1, and they add up to 0. They add up to 1. And so this matrix, P, 1 minus P, 1 minus Q, Q, corresponds to this sort of graph. You have 2 states, 1 and 2, and the way you're interpreting this is that if you're in state 1 with probability 1, in the next level, in the next iteration of your dynamical system, you're still going to be at 1, and with the remaining probability, which is 1 minus P, you're going to switch sides, and so on. What I said was, if you compute the square matrix, so the square of the matrix, which is what is happening at time 2, this entry in the top left corner, I told you would say the probability of staying in 1 in 2 consecutive years. That's not necessarily true. The probability of staying in state 1 is P squared, if you want to do it 2 times. Or, of course, you can go to 2 with probability 1 minus P, and then go back with probability 1 minus Q. So really, this top left corner of the second iterate of your time evolution matrix would tell you the probability of starting at 1 and ending at 1 after time 2, at the end of time 2. Okay, so that's sort of like a minor detail, but it is important. So we were discussing this Ehrenfest dog-flea model. Another name for it is the Earn model. I like this interpretation more, so that's what we're discussing. So you're interpreting, so you're thinking of this. You have two dogs, and each of these dogs have the same amount of fleas, let's say. Let's say in this case 3. And the idea, the model is that each flea jumps to the other dog with equal probability. And after each time step, you're making one of these fleas go to the other side. The idea is that this is a Markov chain, and likewise it can be represented using a stochastic matrix. So your states now are going to be symbols of this form. So when I write it like this, I mean I have initially 3 fleas on the left dog and 3 fleas on the right dog. So instead of first starting to write down the matrix, it's good to sort of draw the graph. It's much easier, I would say, to keep track of what is happening. So with equal probability, this is going to turn into either 2, 4, or it's going to turn into 4, 2. Right? So this transition corresponds to one of these fleas on the left dog jumping over to the right dog. And this transition corresponds to one of the fleas on the right dog transitioning over to the left dog. And in this case, you have 3 fleas here, three fleas here, which means that this is equal probability. It's hard to say 3 fleas. Okay, so if I'm here, now either I can go back to this, or yet again one of these fleas on the left side could decide to jump on the dog on the right. So that would be 1, 5, or this. But you see now the probabilities are starting to get skewed, right? Because it's again equally likely, which means that for this to happen, my probability is 2 out of 6, right? So I need 2 of these, either one of these, to jump over. For this to happen, it is more likely because I have more fleas on the right side. So this should be 4 over 6, and this should be 2 over 6. And finally, I have 0, 6 over here. Somehow, all of the fleas decided to jump on a dog on the right. And so the probability is even more skewed this time, right? So I can go here, or I can go there. The probability here is very low now, because I have only 1 flea. It is very unlikely, but it can happen. And the way to go from here to there is 5 over 6. Okay? And of course, if you're here, you can go back here, and that's the only thing you can do, which means that you want to have an arrow this way with 1 on it. Any questions about how I'm sort of coming up with these numbers? Okay, so you can do the same thing in the other direction. Let me just fast forward this. 6, 0. So it's just going to be symmetric, right? Because there's nothing distinguishing the left dog from the right dog. Then that's 1. That's 1 over 6. Okay. So now I want to store all this information in a matrix. And I want it, so it's going to be a stochastic matrix. So in this situation, we had 2 states, and my matrix turned out to be 2 by 2. In this case, we have 1, 2, 3, 4, 5, 6, 7 states, which means that my matrix is going to be 7 by 7. Okay. So 1, 2, 3, 4, 5, 4, 5, 6, 7. And then 1, 2, 3, 4, 2, 3, 4, 5, 6, 7. Okay, that's my matrix. So the way to store this is like this. I want to say in the ijth entry, I'm putting in the probability of switching from state j to state I. Let me write that. So put the probability of switching j to I into the ijth entry in Sij. Okay? So really this corresponds to, so I guess we need to enumerate this somehow. Let's put some numbers. This enumeration, of course, is arbitrary, but we need some enumeration. Let's say that this is state 1, then this is state 2, 3, 4, 5, 6, and then 7. Okay. So this first row, I'm not going to write all of them. The first column corresponds to state 1. So you start at state 1, you move on to state 2. Okay? So state 2 corresponds to the second row, which means that you want to put 1 here. And everything else is going to be 0. As you can imagine, most of the entries of this matrix is going to be 0. In other words, this is going to be a so-called sparse matrix. That's also an important aspect of this. If you're at state 2, you can go up or down, and everything else is going to be 0. And you can imagine how in this matrix, really all the non-zero entries are going to be above and below the diagonal, except here. So if you have here 1, here 2, which corresponds to state 7, you can only go to state 6, which means that this is 1. And everything else is going to be 0, except these entries. Okay? So let me just fill those in. And then like so. Typically people don't spend time putting zeros in, but let's do it for once. That's it. So I have a bunch of remaining entries. So now I can see that, for instance, switching over from state 2 to state 1, right, has probability 1 over 6. And the probability of switching over from state 2 to state 3 has probability 5 over 6. As you can imagine, whenever I do this, all of these columns are going to be probability vectors. So now this is going to be, so from 3 to 2 is 2 over 6, and this is 4 over 6. From 1, 2, 3, 4 to 3 is 3 over 6, 3 over 6, 2, 3, 4, 5 to 4 is 4 over 6, 2 over 6, so there should be some sort of symmetry, of course. And then this one is going to be 5 over 6 and 1 over 6. Okay? Yet another stochastic matrix that represents this Ehrenfest or Ern model, or dog-flea model. Any questions about this? It's basically the same idea that we're going to use for PageRank. There's going to be a network of web pages Now, there are no fleas necessarily, but there are web pages and they link to each other. And based on those, the number of links, we're going to come up with those probabilities essentially. Okay? I think this is all I wanted to say regarding Markov chains in general, and I want to focus on PageRank. So let me, yes?
How did you place your ones in the spots that you placed them?
Yeah, so for instance here?
Yeah.
Yeah, so I'm looking at state 1, and this corresponds to state 2. Right, so 1, 2, 3, 4, and so on. So this represents the probability of switching from state 1 to state 2. And I look at that, and I read the number.
And then there's no way for you to get from state 1 to state 3, so it's a 0?
Exactly, yes. Yeah. Yeah, so I'm sort of like making, so in my model, I'm thinking that at every time evolution, exactly one flea switches to the other side. Yeah. Okay. So, PageRank. Now recall that this was one important piece of coming up with a search engine. There are generally 3 steps. One of them is crawling. So after all, you don't know which pages are out there. You have these bots, basically algorithms that sort of like try different links and so on, figures out sort of like a structure for the web page. So that's step 1. Step 2 is indexing. You want to figure out certain keywords and so on. These are not the issue with PageRank. PageRank is not really about these. PageRank comes at the 3rd stage. Once your user queries a certain term, you want to first use your indices, your indexes for your web pages and figure out which ones are, first of all, relevant to begin with. Second of all, because there are so many web pages, you want to order them in a certain way. You want to curate, right? So let me just say curate. So when someone types on Google, University of Utah, you want to figure out which web page should be the first web page that should be shown. Let's not worry about ads and all that stuff for now. This is, of course, more classical. But PageRank comes into play here. Okay? And the idea is that, so the importance of a web page should be proportional to the importances of the web pages that refer to it. Okay? The ranking or importance of a web page should be proportional to the rankings of web pages that point to it, that link to it. So having your, so getting a link from an important web page should be more important for your web page than getting a link from a random web page. That's the first idea. Second idea is that in this contribution, the more a web page has links to other web pages, the less it should contribute. So this is idea 1. So maybe item 1. And then the other item is the more outlinks, let's say, outlinks a web page has, the less it should contribute to each of these web pages' rankings. To the rankings of these web pages. I should mention this is not the only algorithm out there that people use to rank web pages, but this is the one that sort of became most famous. It seems around the time that Brin and Page came up with this, it was in the air basically. A couple people were sort of looking into this. They just turned it into a business, essentially. Now, I'm going to write down the general equation in a second. But before that, let's look at an example. We had already done this in the first class of this course, but let's look at a simpler example. I mentioned at the time that there are certain bugs with this. And there still are bugs. We're going to have to adjust it a little bit. But let's start like this. Yeah. So let's look at this, for instance. So here's a network of web pages consisting of 4 web pages. So I have 1, 2, 3, and 4. And this is how it looks like. Okay? I should also mention that this ranking, all of these, so what I want to do here is that I want to have a PageRank vector. It's going to be a probability vector of 4 entries. And pi, or the ith entry of the PageRank vector, is going to be the ranking of the ith web page. So PageRank vector is going to be P, P1, P2, P3, P4, and it's a probability vector. The ranking of the first web page, I'm going to write it over here, I think. So the probability, so the ranking of the first web page should be completely determined by the rankings of the third and fourth web page, because these are the only two web pages that point to it. Right now, I'm not going to write the equations. I'm just going to write it like this. So this should be like this: P3 plus some number times P4. Okay. The only web page that links to 2 is web page 1. Okay. So the page rank of the second, so the ranking of the page rank of the second web page should be proportional to the page rank of the first web page. How about 3? 3, so web page 1, 2, and 4, they all have links to web page 3. So the page rank of web page 3 should be some linear combination of them. And then finally, P4, so the page rank of 4, should be completely determined by the page rank of 1 again. Oh, yeah, also P2. Yeah, sorry. I missed it because there's also a link here. Thank you. Of course, at this stage, we recognize this as a system of linear equations, and it's a matrix after all. Once I sort of factor out this P vector, or the entries of it. So this is the first stage. So far, we use only this assumption, right? So the ranking of a web page should be proportional to the rankings of the web pages that link to it. But then I want to adjust these numbers. I just don't want to count. I don't want to count only the number of links that a web page has into it. I want to say something like this. Because, for instance, web page 1 has 3 outlinks, it should equally distribute its own page rank. Which means that if I'm sort of like trying to come up with a Markov chain, the density, the weights on these arrows should be 1 over 3, 1 over 3, 1 over 3. Okay? So that means that whenever the first web page contributes to some other web page, it should be 1 over 3 times that, times its own ranking. And here too. Okay. Likewise, so the second web page links to 3 and 4. It has 2 outlinks. So I should divide, when I'm contributing, when I'm adding these contributions, I should divide by 2 whatever the ranking of this is. So here I should see 1 over 2. And here I should see 1 over 2. For 3, it only links to 1. So I'm not dividing it by anything. So it's just 1. For 4, it links to 1 and 3. So whenever I see P4 here, I should be dividing it by 1 over 2. Okay? This is essentially the idea. Now let's write it using, write the system using matrix notation. Okay, so this is 1. This is 1 over 2. And then this is 1 over 3, 0, 0, 0. 1 over 3, 1 over 2, 0, 1 over 2. 1 over 3, 1 over 2, 0, 0. Okay, so that's, again, a stochastic matrix, as you can see. Each column adds up to 1. And I'm thinking of this as a probability vector as well. So this is called the hyperlink matrix for the network of web pages. It's a stochastic matrix. I'm going to call it H, and this is P. Okay? But of course, this is nothing but, once I use these abbreviations, this is nothing but this. Well, this is nothing but the eigenvector equation for H associated to the eigenvalue 1. Okay, so this is the important step. So we know that there's such a vector, right? So okay, let me back up a little bit and go talk about this slowly. So the PageRank vector is a probability vector that is also an eigenvector for the hyperlink matrix of whatever web page network you're looking at, associated with the eigenvalue 1. Eigenvector of the hyperlink matrix H of the network of web pages in question associated to 1. Okay, so this is the main idea. Any questions about this so far?
I kind of have a question.
Yes.
If I was thinking about this like from the perspective of writing code,
Yes.
I would think that there'd be like a circular dependency
Yes.
between like the probabilities, because to figure them out you need to know them.
Yes.
So I'm sure you'll probably talk about that.
Well, that circular dependency is encoded in here.
So it's not a problem?
No.
Okay.
In fact, that circular dependency is what makes it work. Whenever you don't have that circular dependency, PageRank, so this, the way I described it so far, doesn't work. So my aim is to keep adjusting this model so that ultimately we reach the version that was patented. Yeah. This doesn't quite work exactly. In this case, it does work, but in general, it may have issues. Any other questions about this? We're going to discuss those issues in a second.
The question, the point on the upper left there,
Yes.
how do we justify that? Because I would think that the more outlinks of the page the more it is called for reference.
Yes.
The importance is high.
Yes, its importance is it's determined based on this. So think of think of this network as a hydraulic network. And I'm talking about like how water flows. It's like a limited resource. Whatever the PageRank of this guy has, and however many links it has to distribute equally. In a hydraulic network, it's more complicated, of course, because you can talk about, like one link has a more capacity and so on. And in information theory too, you can look into that. But for now, we're just saying each of these hyperlinks can handle the same amount of flow. And everything, so the importance is a finite resource. So you have to divide it.
Okay, so that's the extra ingredient of the finite resource involved with the network.
Yes, essentially. I mean, so you can just start with this, okay? And of course, I didn't tell you the probabilities here, but you want to turn it into a probability. So you want to sort of like turn it into a Markov chain. The simplest way of doing this is to say, 1 has a link to 2, 3, and 4. I'm just going to say the probabilities are equal. So that's sort of one way of thinking about this. Yeah. And of course, even though I'm using this, interpretation of this as a network of web pages, it can be pretty much anything. Whenever you have sort of like a network or something, you can, and people do indeed, use something like this. You can use even something like this to detect fraud in healthcare. People do that. So because ultimately, PageRank is all about looking at a network and figuring out which of these nodes, as they're called, is the most important. So, yeah. Any other questions? Okay. Now, I mentioned that there are certain issues with this. There are theoretical issues, and there are practical issues. Practical issues are mostly about being able to compute this. Okay? So, that is to say, being able to solve a system of equations. But you can imagine how, in this situation, there you have a lot of web pages, which means that this matrix is humongous. Okay? So you don't want to sort of solve the system, essentially. We sort of discussed this. It's the cost of solving a system like this is of the order n cubed. So if you have 4 web pages in this case, it would take you approximately 4 to the 3, which is 64 operations. If you had 1 billion web pages, now that would be, the order of magnitude would be 3-fold. So that's not good. So that's why what you want to do is not solve the system and somehow set up an iterative system, iterative algorithm. And so this is where this so-called power method comes into play. We sort of discussed this last week when we were discussing dynamical systems, but let me just remind you or be more explicit about it. We take an arbitrary square matrix. Let's take an eigenvector, let's say lambda 1, eigenvalue. Say for any other eigenvalue, this happens. Okay? So on the picture, let's say that your eigenvalue is here, lambda 1. You want everything else to be closer to the origin. Okay? Okay, I'm going to... There's a way to state it this way, but maybe I don't want to state it this way. I'm going to change it. Because otherwise I would need to normalize it. Okay. Say 1 is an eigenvalue. And if you have another eigenvalue that is not 1, then it is inside the unit disk. Okay. So this is the picture for the spectrum. We have this eigenvalue, which is 1, and everything else is inside. Okay, I don't care where they are. All I care is that they're away from this, from the circle. Okay. Then the power method says that if you start with any vector whatsoever, for any v that is non-zero, if you keep iterating a, so under this dynamical system, it's going to converge to an eigenvector. So a nv converges as n goes to infinity to an eigenvector. Associated to 1. Okay, so here's a simple example. Oh. As to why this should be the case. So here's an example. Taking a very simple diagonal matrix. Of course, this satisfies what I want. So one eigenvector is this. The other one is this. Okay? And recall that this is not a stochastic matrix. The columns don't add up to 1. But that's not an issue. Now, if I were to start with any vector, right, it would be of the form AB, which I can write as A times 1, 0 plus B times 0, 1. And of course, 1, 0 is an eigenvector associated to this eigenvalue 1, and 0, 1 is an eigenvector associated to the eigenvalue that is less than 1. Okay? I didn't tell you what B is, and I know that in this case, I want to sort of come up with 1, 0 somehow, because I want to end up with an eigenvector for 1. But instead of just saying, trying to compute it, what this power method says is the following. Look at this. Let's be even more specific. 5, 7. Certainly, this is not an eigenvector. It's some vector. And I'm taking pi powers of it. So I'm taking nth power of A multiplying by V. And so what is this? This is 1, 0, 0, 1 over 2 to the n times 5, 7. Which is 5, 7 divided by 2 to the n. Okay? Now you see, as I take n to infinity, the second component is going to vanish, and I'm going to be left with 5, 0. That's an eigenvector. That's the idea behind the power method. It's very simple, in a sense. Instead of trying to solve it, we just keep multiplying. And of course, instead of taking the nth power of the matrix, which is equally as expensive as solving the system over there, what you do is you do the matrix vector multiplication. So instead of first multiplying A n times by itself and then by V, you do this. You start with V, and then you compute A times V. Now, the cost of this is of the order n squared. So it is cheaper. And so on. That's how you compute things. And another important thing here is that how fast this approximation happens is of an exponential order. And of course, this exponential is about how large the second eigenvalue is, right? So if instead of 1 over 2 here, I wrote 9 over 10, well, 9 over 10, or powers of it, decays slower than 1 over 2, okay? So this here, this distance here, is also important for practical purposes. We're not going to discuss too much about that, but I just wanted to mention it. So you want to be able to use the power method to find this solution, okay? There's another issue. So now there are the theoretical issues. You want to make sure that no matter where you start with, so which vector you start with, when you do this power method, you reach the same vector, okay? Now that requires that not only is 1 an eigenvalue, which is guaranteed insofar as H is a stochastic matrix, but that its geometric multiplicity too is 1, okay? So it's a simple eigenvalue, is what they would say. And the third thing, of course, is that because I want my ranking vector to be a probability vector, its direction should be controlled as well. It should be in the first quadrant. So these are the main ideas, main problems. So let me write it. Once. Use power method to find P and here. I want that the geometric multiplicity of 1 for this hyperlink matrix is 1. And of course the algebraic multiplicity I want it to be 1 as well. Now there's this whole theory called the Perron-Frobenius theory that essentially gives you conditions where this is guaranteed. We're not going to go too much into that because there's some terminology that we would need to develop and so on. I just want to go through some examples and figure out where things can go wrong and so So this means that the PageRank is going to be unique. So okay, these are the two main issues. Now, for this link network of web pages, it turns out that things work out fine. So for this, you can indeed use this iteration method, or power method, to just keep pushing, and you're going to be able to compute the PageRank vector, and it's going to be a unique vector. But there are some other networks where this doesn't work. Specifically, there are two main issues. And that's about the non-distribution of importance. So we sort of talked about this circularity of PageRank, or this sort of equations. If you don't have circularity, which means that if you're leaking your importance somewhere, then the way I described it doesn't work. So now you need to do some adjustments. So here's an example. That's a very simple web network. I have two web pages. Only one refers to the two, and there is nothing else. But you see now, when I look at the hyperlink matrix, it's a 2 by 2 after all. So one goes to 2 with 100% probability, and everything else is 0. You see now, this is not a stochastic matrix. This column is a probability column, but a probability vector, but this is not. Okay, so that's an issue. You can still write down the equation and try to solve it. But what's going to happen is that the second web page is going to have 100% importance, and the first web page is not going to be important at all. Now, for 2 web pages, that's not an issue, but of course, when it's more than 2 web pages, things are more complicated. On Friday, we're going to go more into detail about this. I'm out of time, unfortunately. Thank you. I'll see you on Friday. Okay, let's start. Good morning. So this is our final class that will be recorded next week. We have 2 classes. Those are going to be not recorded, and they're going to be reviews. Yeah. Maybe at the end of this class, if we have some time, I want to sort of go through what we did and what we ended up not covering. We covered most of the things that I wanted to cover, but in any event. So we were discussing this PageRank algorithm, or paradigm, let's say. So now I'm giving you here the sort of definitions more rigorously. We were already using these definitions in the examples that we were discussing on Wednesday. Just wanted to write everything down explicitly. So you start with a network of web pages, which I denote by n. So the term of art really for this is a directed graph. N, lowercase n, is going to be the number of web pages. And instead of web page, if you're looking at a general directed graph, you call whatever the analog of the web page is a node or a vertex for the graph. So if I have a web page I, then I associate to it 2 different sets, in of I and out of I. In of I is, well, it's the set of all those other web pages that link to I. And out of I, well, it's the set of all those web pages that oh, I wrote it the other way around. So in of I should be all those web pages that point to I. So j going into I, and out of I should be all those web pages that I points to, has a link to. So given a network, or more generally a graph or directed graph, you get to associate certain matrices to it. And based on this, you can apply linear algebraic methods to discuss properties of this network. Two of the matrices that we are using are called adjacency matrix and the out degree matrix. Okay? So the adjacency matrix basically keeps track of which two web pages are connected, and out degree matrix keeps track of how many outlinks you have. In a second, I'm going to do an example and compute all of these explicitly in an example. But for now, let's just take it for granted. And then once we have the adjacency matrix and the out degree matrix, if you compute this, the inverse A. Now, note that in this case, both of these are going to be n by n matrices. N is the number of web pages. H2 is going to be an n by n matrix. And if you write it out, it is this matrix. So if there's a link from j to I, its entry is going to be 1 over the number of outlinks that j has, and 0 otherwise. And this is the PageRank equation that we were using so far. H is my n by n hyperlink matrix, and I'm looking for a vector that is fixed under it. And I want that vector to be a probability vector. That vector I call the PageRank vector. And recall that the definition of a probability vector is that it's a vector, all of whose entries are non-negative, and they add up to 1. So I can think of each entries as certain probabilities of a certain state happening. In this case, a certain web page, or being on a certain web page. So the three issues with this, we're going to discuss this more in detail today too, are these: dangling nodes, rank sinks, and issues with the power method. Before I get into that, let me just do an example and write these things explicitly so that it is clear that we're sort of, this is nothing new. So, let me think. Oh well. Let's, for instance, consider this. My network is going to have, let's say, 3 web pages, and here are the links. Let's say 4. Okay. And then you have this, and then that. Okay, that's a valid network of web pages. It consists 4 web pages. So n is 4 here. Now all of these matrices are going to be 4 by 4. So let's look at this. Insets and outsets. So so here I want to record all those web pages that have links to 1. When I look at this, I see that only 2 has a link to 1. Okay, so that consists of only 2. If I look at 2, as you see, both 1 and 3 have links to 2 and nothing else. Three has links from 1 to 2. And 4 has a link only from 3. These are the insets. The outsets are like so. Now I'm looking at the other question, right? So which other web pages that 1 points to? 2 and 3. So that this should be 2 and 3. Um, 2 points to 1 and 3. Three points to 2 and 4. Four doesn't point to anything, so it's empty sets if you want. Okay. Next, the adjacency matrix. So it's this A matrix over there. So I'm going to put 1 if I have a link from J to I, otherwise it's going to be 0. So this is a 4 by 4 matrix. So I'm looking at the first web page now. First web page has a link to 2 and 3. So that's 1, this is 0, this is 0. Second web page has a link to 1 and 3. Third web page has a link to 4. Fourth web page doesn't have any links. Okay. Next, the out degree matrix. Well, this time it's going to be a diagonal matrix. That is again 4 by 4. And here I want to put the number of web pages in out of 1. So that's 2. The number of web pages in out 2 is 2 again. Then again it's 2, then it is 0. Okay. So next step is to compute the hyperlink matrix. Which is D inverse times A. But of course, you see 0 is an eigenvalue, or its determinant is 0, which means that D is not really invertible here. Really, when I write it like that, I mean sort of the best possible thing you can do with inverting D. It's called a pseudo-inverse. In any event, by this multiplication, I really mean this. Invert D as much as possible and leave the rest as 0. So this is going to be 1 over 2, 1 over 2, 1 over 2, 0, multiplied by A. So maybe I should do it here. Okay. That's my diagonal matrix. Let me not write the remaining zeros. And then I have this. 0, 1, 1, 0. 1, 0, 1, 0. 0, 0, 0, 1. And then this is 0, 0, 0, 0. And of course, taking a matrix and multiplying it from the left by a diagonal matrix corresponds to scaling the corresponding entries by whatever number you see there, which means that you're going to see this. Yeah. Yes, it should. So I forgot then. Yeah. That should be a 1. Yeah, I did put it there. Okay. Thank you. Okay, so this one here corresponds to this hyperlink. Okay. Yeah, so now writing this down, we get this. Then 1 over 2, 0, 1 over 2, 1 over 2, 0, 0, 0, 0. I think I made a mistake somewhere because I want this to be 1 over 2. Okay, let me think. So ultimately, I want this to be my hyperlink matrix. First of all, the first web page, so the first column works fine, because I should have 1 over 2, 1 over 2. Second web page goes to 1 and 3. Third web page goes to 3 and 4. Sorry, 2 and 4. So this should be a 1 over 2. And 4 shouldn't have any non-zero entries, because 4 doesn't have any links to some other web page. So somehow I have an issue here. Let me have a look. Well, in any event, there is something weird going on here, but this hyperlink matrix definition is accurate. So this formula over here, Hij, is accurate. Somehow D inverse A is not really giving me what I want. So there's an issue with this entry. I wouldn't have to think about it, but if I can figure it out later, I'll send an email. But in any event, this is sort of what we've been doing so far. The three issues with this are these. So whenever you have a web page that doesn't connect, that doesn't have a link to any other web page, that's called a dangling node. So this is a dangling node. Okay. Looking at the hyperlink matrix, you see zeros in the column that corresponds to any dangling node. Now, based on this idea of the random surfer, which basically means that you start at any web page, and with equal probability, so you think of it as a Markov chain, with equal probability, you go to any one of the web pages that the web page you're at currently links to, right? So if you start at 2, so 50%, so with 50% probability, you go to 1 at the next stage, or to 3, and you keep going on like this. But ultimately, the idea is that there's some probability, there's 50% probability if you're somehow at 3 to go to 4, and then you're stuck. If this happens, what's going to happen is that this dangling node is going to take all the importance out of the system, and your PageRank vector is going to be 0, 0, 0, 1. It's a probability vector, that's fine. So the math is not really an issue, but it's not really telling you the rankings of the other web pages. Another thing, of course, is this issue with sort of getting stuck at different dangling nodes. If you have multiple dangling nodes, then depending on where you start your random surfing, you might end up at weird places or at different places. So it wouldn't be sort of like this authoritative PageRank. You wouldn't be able to come up with a ranking like that. So somehow you need to do something about this, okay? That's the first issue. So let's, so based on this random surfer idea, I told you that no matter where I start, ultimately I'm going to get stuck at 4, and I'm never going to be able to leave, which means that pretty much most of my time will be spent here. And in fact, when you take sort of like longer and longer averages, it's going to turn out that all of your time is going to be spent here. The spent that you spend here is going to be negligible. And looking at this, you can also immediately see that yeah, so it's still not a good thing. There's something confusing about this example, but in any event. So you want to do some sort of pre-processing to handle those columns of zeros and turn your hyperlink matrix into a stochastic matrix. So the way it is right now, this hyperlink matrix is not stochastic. The first column has no issues. Everything adds up to 1. Second column too has no issues. Third column has no issues. But the fourth column that corresponds to the dangling node is 0. So that breaks the stochasticity. So the hyperlink matrix ends up not defining a Markov chain. This is coming from the dangling node. And makes the hyperlink matrix not stochastic. If there are H is not stochastic. Okay. The second issue is sort of like a generalization of this first idea. And maybe I should multiply D inverse A the other way around. So it should be AD inverse. It should be one of these, one of the two. So the second issue is the issue with rank sinks. So let me adjust this a little bit. So for instance, consider this. Yeah. Let's just, yeah, okay. Let's say it's like this, and then I have this, and then I have something like this. So now I have 5 web pages. In this situation, what I call a rank sink would be 1 and 2. Okay? So this would be a rank sink. So this is sort of like a sub-network of your larger network that is consistent by itself, but it doesn't lead to somewhere outside. Using the random surface model, you can say, oh, no matter where I start, right? Ultimately, there is some probability, right? Because there are links. There is some probability that I'm going to land on 3, and then I'm going to have to move to 1 or 2. And then I'm going to be stuck here. Okay? And so ultimately, that means that most of my time is going to be spent between 1 and 2. I'm going to keep sort of like oscillating between 1 and 2. This oscillation is not really the main issue. The main issue is, or at least for this second problem, the main issue is that now 1 and 2 is going to suck up all the importance of the system. And your PageRank, you will be able to compute it, but your PageRank vector is going to give you 0, 0, 0 here. Okay, indeed. So if you look at this, so it's going to be a 5 by 5 matrix. 3, 5. So 1 points to 2, 2 points to 1. So this corresponds to 1, this is 1, this is 1, everything else is 0. What is the issue this time is that in terms of linear algebra, we have this block of zeros. Okay? Now we have, like, we can complete this hyperlink matrix. It's not, that is not really an issue. From this, you can immediately see that 1 over 2, 1 over 2, and then the rest zeros is going to be a PageRank vector. So P equals this is going to be a PageRank vector. Right? So, and it makes sense using this random surfer model as well, because all it says is that, so ultimately you're going to end up at 1, 2 in this cluster, and 1 and 2 should have the same rank because they're basically symmetric. 1 sends to 2, 2 sends to 1. The issue with this is that probably it might be a good idea to rank the remainder also. You don't want to say, oh, 3, 4, and 5 both have rank 0. So that's sort of like the issue. The third issue is slightly more subtle. So maybe I should record that as well. So if there are rank sinks, then we can say that most pages will have rank 0. Which means that they are indistinguishable. But you want to be able to distinguish as much as possible. The third is more subtle. So for this, let's look at this example. I'm thinking more and more that this should be A times D inverse, not D times A inverse. But so here's an example. And this is a very simple example, but I think it is illustrative. I have 2 web pages. 1 points to 2, 2 points to 1. Okay? Hyperlink matrix is this permutation matrix. It's 2 by 2, stochastic. It's nice. Okay? One is an eigenvalue. It's a simple eigenvalue, right? So it doesn't. So its algebraic multiplicity is 1. Can you immediately see what the other eigenvalues based on some heuristics? Yeah. How did you, do you have sort of like a way to figure that out? Like how did you figure that out?
I just did it in my head. I just
Computed?
Yeah, negative lambda.
Oh, okay. I see, yeah, yeah. Yeah, you can compute it that way, or you can think of it like this. So you can think of geometrically. Geometrically, this flips x and y axes, right? So it's a reflection along y equals x. Okay? Which means that it fixes y equals x, which means that any vector whose components are the same is going to be an eigenvector associated to 1. This is a symmetric matrix. By the spectral theorem, eigenspaces have to be orthogonal. So the other eigenspace is this, y equals minus x. Okay? You can think of it that way as well. So in any event, one eigenvalue is 1. The other eigenvalue is minus 1. So that's an eigenbasis. So for the power method, recall that what we did was the following. You take any probability vector whatsoever, that's your initial sort of test probability distribution, and you keep iterating h. Right? You think of it as a dynamical system. You say, ultimately, when I keep iterating h, it should converge to a solution to this. So you set up this. So let me write it like this. You start with some initial probability. You sort of come up with something. You just figure something out. And then you keep iterating. So you say P of m plus 1 equals h times P of m. And you hope that for large m is your time now. For large m, this sort of like gives you a good approximation for your PageRank vector. But the problem with this is that in this case, this procedure is going to be very volatile. Let me just erase this. The power method is volatile. That's because, so you have, let's say, V1 corresponding to eigenvalue 1 and V2 corresponding to eigenvalue minus 1. That's a basis. You can write any condition like that. So let's say this is C1 times V1 plus C2 times V2. This corresponds to iterating h m times and applying h to that. So h to the m of P0 is going to be now C1 times V1, right? Because V1 is an eigenvector associated to the eigenvalue 1. So this part is going to stay the same. The second part is going to keep oscillating between plus and minus, because V2 is an eigenvector associated to minus 1. So this is going to be plus or minus C2 V2. But in order for power method to work, what you want is that you want every single piece that corresponds to eigenvalues less than 1 or non-1, let's say, to decay, so that ultimately you only end up with you end up with this. So this is the issue. For the power method to work, what you want is that you want this piece to decay as you take m to infinity. Okay, so these are the three main issues with this basic PageRank algorithm that I wrote. Any questions about this so far? So the answer to this is to essentially add some noise to the system. Okay? So this PageRank is supposed to be something like a Markov chain, which is sort of like a probabilistic model, but you want to sort of like add some further noise to it. And this is sort of like a general idea. Whenever something doesn't work, you add a little bit of noise, and now it works, paradoxically. So modified PageRank. We're going to build on what we have already. First of all, you want to have a pre-processing scheme so that this hyperlink matrix is not a non-stochastic matrix. So you want to handle these dangling nodes somehow. There are a couple of ways of doing this. The scheme that I think is most popular is the one so-called disperse. So first, transform H into a stochastic matrix. And the way you do this is by replacing any 0 column with the uniform probability. So in this case, I would want to put 1 over 4, 1 over 4, 1 over 4, 1 over 4, 1 over 4. I want to have a probability here, and I want each probability to be the same. This is not the only way of doing this, but this is one method. There are multiple methods of doing this. So replace. So this is a disperse transformation. Replace any 0 column with 1 over n, 1 over n. Now, what does this mean in terms of the network? It means that if you have a web page that doesn't have a link to anything, you just pretend that it has a link to everything, even itself. So let me here demonstrate in this example. So 4 was our only dangling node, and here, as you see, in the matrix, we saw this. Now I'm applying the disperse scheme. Okay, so now from 4, I add these virtual links. Okay. So you're saying I'm going to disperse whatever rank I get to back into the system. This is not really the version that Brin and Page used. What they do is they sort of like just get rid of any dangling nodes. They just pretend that they don't exist. But this seems to be more popular among sort of in the literature, so let's just stick to this. So which means that here, now my new hyperlink matrix is going to be this, but now this is going to be all 1 over 4s. Okay, so now you see the hyperlink matrix is guaranteed to be a stochastic matrix. If you have multiple dangling nodes, you apply the same thing to each one of them. Okay, that's the idea. Any questions about this? This is the first modification. Second modification is to now start adding some noise. And this is also where you introduce personalization. I can erase this. I take a parameter alpha between 0 and 1. Okay. This is called the damping factor. And I'm going to take a probability vector B. That's going to be my bias vector, or personalization vector. Okay, so now I define this Google matrix to be G, which is a linear interpolation between the sort of processed hyperlink matrix, let me call it H hat, and a rank 1 matrix that I obtained from this personalization vector. Alpha times H hat plus 1 minus alpha times B times 1 transpose. So 1 in Blackboard font is the so-called vector of 1s. It is the n by n vector, each of whose entries is 1. I take the transpose, so now I'm multiplying an n by 1 matrix with a 1 by n matrix. So this gives me an n by n matrix. It's stochastic because B is a probability vector. Each column of this is the same vector, essentially. Okay? So once you do this, you see now you have two different behaviors. In one of them, you have sort of the structure of the network. And in the other one, you have some personalization. I'm going to give examples of how this would work and why it would be called the personalization vector in a second. But let's for now take it for granted. So what you're doing is, and you have this damping factor. The way you interpret this Google matrix is this. With alpha probability, so let your random surfer act according to the network, according to the structure of the network. With the remaining probability, act according to your biases. Okay, that's the idea. So with alpha probability, act or surf, according to the structure of the network, and with 1 minus alpha probability, act or surf according to your biases. With 1 minus alpha probability, so the larger alpha gets, so the closer alpha gets to 1, the more you're emphasizing the structure of the network. The more alpha gets to 0, the more you're emphasizing the bias. Okay? And the point is to find sort of like a nice balance here. And Google, so Brin and Page, initially used the alpha as 0.85. And there's a lot of research about what this alpha really does and so on. It's a wonderful topic, but I think so far this much is enough. So what do you do with this? With this, now you say, instead of looking at an eigenvector for H, let me look at an eigenvector for G, this modified matrix. Let me write that here. the true definition equation is, well, GP equals P. P probability. We don't have much time to discuss this, but the main idea is that if alpha is slightly less than 1, like it doesn't need to be exactly 1, or it can't be exactly 1, but insofar as it's some number toward 1, and B, the bias vector, has all of its entries non-zero, this has a unique solution. It has a unique eigenvector and the correct configuration, and the power method works. Okay? And indeed, it turns out that the smaller you take alpha, the better the power method works. So there are multiple trade-offs here as well. And so this is the idea. So now let's think about an example and where or how I would do this modification. Yeah, so for instance, let's take this example. Let me add one more, or maybe let me adjust it a little bit so that it's easier to write. So I want to keep that rank sync over there because I want that to be an issue. Let's keep 3 as well. I'm going to erase this. Oh, I'm going to put this. Okay? And let's say I have another 1, 6 here. So this is my network. Now I have a 1 rank sync here. That's an issue. I have 2 dangling nodes. That's also an issue. And inside this rank sync, I also have this issue of the convergence of the power method. Okay. So first writing the hyperlink matrix. So now it's going to be 6 by 6. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So 1 points to 2, 2 points to 1, as we discussed before. Three points to 1, 2, 4, 6. So I need to divide everything by 1 over 4. So 1, 2, 4, 6. And the remaining 0. 4 points to 3 and 5. So 3, 5 divided by 2. 5 doesn't point to anything, so that's going to be all zeros. 6 doesn't point to anything, that's going to be all zeros. Now I apply my pre-processing procedure to turn it into h hat. H hat, so before these entries were all zeros, now they're all going to be 1 over 6s. Okay, so now it's a column stochastic matrix, as you can see. Any questions about this so far?
So the dampening doesn't deal with the rank sync like we do that with something else?
Yeah, exactly, yes. Yeah, how you're handling the rank sync, or how this linear interpolation handles the rank sync, it's slightly more, like it requires more theory. This is more straightforward to see. let's just take that for granted that that indeed works. So this is the first stage. Second stage, I need to come up with a damping factor. I'm not going to compute it, of course. And there are problems in the problem set where I'm asking you to do these changes. But whenever there's an actual computation, you're allowed to use a computer algebra system, of course. And indeed, one of the problems in the last problem set is to come up with the highest ranking web page for this class. So you're going to model the links for this class and figure out which is the most important web page, which web page is the most important. But in any event, so let's say that alpha is the traditional one, 0.85. So now I need to come up with a bias vector. It's going to be a 6 by 6 6 by 1 matrix. So for instance, I can say the following. Certainly I can use 1 over 6s all over. My bias vector is no bias, essentially, unbiased bias vector if you want. But I can do something like this too. Let's say that I want to say that, oh, this user really likes, for whatever reason, this web page. This is, let's say, this user's home page. Okay? So when I'm thinking of the random surfer, I want to think like this. With this 1 minus alpha probability, my surfer is just going to click, like home page, and just like teleport back into his home page, and keep going again. So if that is the case, my bias vector would be 0, 0, 1, 0, 0, 0. Okay? So I'm adding bias to this third guy. That's the idea. You can do a bunch of different things, of course. If, let's say, the other one is 4 is sort of like Reddit, let's say, and then this user likes going to Reddit with certain probability and so on. You can do a bunch of different things with this. And then when you compute B times 1 transpose, this is nothing but this vector duplicated so that you have a square matrix. Yeah. 1, 2, 3, 4, 5, 6, and then all zeros, all zeros, all ones, all zeros, all zeros, all zeros. The point is that this is again a stochastic matrix, as you see. And then you compute this G, which is alpha times h hat plus 1 minus alpha times B, 1 transpose, and then you solve the eigenvector equation. The hope is that all these adjustments really help you find this using either the power method or some other thing. Okay? This is all there's to it. I mean, there's more, of course, but I think this is sufficient detail.
Wouldn't the whole thing break if one of the dangling nodes had a pointer to itself?
No, not really. That would be sort of so typically you don't consider web page links that are from the same web page to itself. You just like disregard them. But if you were to consider those, that's still not a major issue. You can still handle those. Yeah. So in the language of Markov chains, that would be sort of absorbing nodes, essentially. Yeah, I think I'm out of time. Thank you. This is it. I'll see you on Monday. We're going to do reviews.